Hiya. So in this video, we're going to be talking about volumes and how we can calculate them using determinants in 3 dimensions. So this is very similar to the last video, but we're going to look at everything in 3 dimensions. So I'm going to go a little bit faster in the sense that all of the ideas and everything there are very similar. So what we're doing this time is instead of starting off with 2 dimensions, we're going to look at 3 dimensions, and we're going to start off with 3 vectors. So 2 vectors in 2 dimensions to get an area, 3 vectors in 3 dimensions to get a volume. So what does that give us? What we have is, so say we have some A, some B. So this will give us a bottom part, right? So this gives us one parallelogram. And what we're going to do is we're going to add some C. And here you really want to consider this in like 3 dimensions. So what I'm going to do to kind of help with that is I'm actually, if it lets me, I'm going to redraw these 2 lines as dotted lines to kind of imply that they're behind in some. And then we draw the parallelogram again. Then hopefully it wasn't too bad. There we go. So this is A, B, and C. And you can kind of see this is forming a parallelogram. On the bottom here, so this little bottom area here, you can kind of see this is the area, right? So this is our parallelogram, A, B. And so we're going to denote this by this fun little formula, which you're going to have a fun time watching me draw every so often. ABC for this parallelogram. So this parallelogram here is given by this image here. And you can kind of see B and C on the bottom. Or I guess I put A and B on the bottom, but in the notes we have B and C. So here you see that the height vector, so if I look at a height here, do this in a different color. So if I look at like a height vector here, H, you can kind of see this is going to be orthogonal to the bottom half. So I guess actually to make these match with the notes, I'll rewrite these so that it makes a little more sense when you're looking at this. We'll make this A needs to be up, A on top, and then this will be B and C down here. We'll do this just so it's the same as the notes. And then this one's hidden, so I'll just write it over. So here we have an H vector, which is giving me the height of the parallelogram. And if you recall from back in the day, in essence, what you want to do is you want to grab the area and you multiply by the height, and that'll give you precisely the area of the parallelepiped. So this is called a parallelepiped, by the way. I don't remember if I said this. It's a fun little word to say. Try to say it 97 times fast. And if your tongue doesn't fall off, congratulations. So let's actually show this. So basically what I'm saying verbally is that the volume of the parallelepiped, look, see, I'm telling you, this is my drawing. It's going to be good enough. Of A, B, C. What I'm basically saying is, okay, what is this? This is equal to the area of the parallelogram on the bottom times the height, right? The height here is the length of the height. So what is this? So here the height is going to be precisely, this is just going to be the A vector here, right? Times the angle that it forms with the other things, right? So cosine of theta. Now, from our previous proposition, so proposition 1.87, what we have here is that this area is really just the cross product of B and C, a cosine of theta. And this you should recognize as an inner product, right? We have cosine of theta, we have B cross C. Since theta, minus theta and plus theta for cosine is the same, this absolute value doesn't really tell us too much. So in other words, this is just the inner product of A and B cross C. Oop, why did I put a, there we go, B cross C. And we want the absolute value here because we don't know which direction it's going since it's the same. So let's actually look at this in terms of an orthonormal basis. So we have this is nice. So here, if we have an orthonormal basis, like we normally do, and we look at everything in matrix form, well, what is this going to give us? So let's write this out again. We have our fun little parallelepiped on top of A, B, C. Now we just noticed that this is A, B, C. Yeah. And this we can convert into matrix form, right? So let's convert these into matrices. So this is A1, A2, A3 dot product with the determinant of B2, B3, C2, C3, the minus determinant of B1, B3. I have a little cheat sheet. I'm sure you all know this all by now. Because I do not have all of this. B2, C1, C3. We have this determinant. And where is this kind of coming from? This we're just doing the dot product, right? So if you kind of think of this, right, we have A1 times the determinant of B2, C2, etc. Oh, here I need a transpose, I think. Oh, no, the determinant. Yeah. So we can kind of see it this way, right? So yeah, this is actually exactly what we're doing. So here, A1, we're going to be multiplying with this determinant, A2 with this determinant, and A3 with this determinant. And then this, when we actually do this out, what do we get? We get A1 determinant of B2, B3, C2, C3 minus, because we have a minus sign for the determinant here, in case you can't see that, A2 of the determinant B1, B3, C1, C3 plus A3 of the determinant B1, B2, C1, C2. Now this you might recognize, but you also might not. And this, if you kind of look at this, you have a plus, you have a minus, you have a plus, and it's A1, 2, 3, and notice how the 1 is missing in the first column, 2 is missing in the second one, 3 is missing in the third one. This is nothing more than the determinant of the matrix itself. A1, A2, A3, B1, B2, B3, C1, C2, C3. So we get this nice little formula. So basically what we just showed is that putting everything together, the volume is given just by the absolute value of the determinant. Again, we take the absolute value because we don't know which way the signs are going, and volume can never be negative. So this is useful to consider like the algebraic area of a parallelepiped. So, this is a separate remark, sorry. So like, even though we're talking about things like volume, area, etc., always having positive area, it does make sense sometimes for us to talk about some, like algebraic area. So in other words, something that has positive area or negative area. And you might be used to this from like calculus classes, for example, where if like you're taking the integration, if you're taking the integral, you want to look at the area under the curve. This would have positive area, and here would have negative area, right? So like, it's a little weird to say negative area, but you can kind of see it is useful sometimes. So we will sometimes do that, and in that situation, we would look at A inner product with B cross product C without the absolute value. So when we do want to consider that, we'll do it without taking the absolute value. So we're gonna finally state basically the same thing we did last time with linear operators. So what happens when we have a linear operator? A very similar thing from last time. I thought this video would be faster, but apparently not. So basically what we end up having is precisely this. Yeah. Ooh, that one was nice. A, B, C. Exactly from before. And the argument for this is almost identical. So it's not really too much. You just like take the volume, you split it up into the determinants, Then you do the matrix multiplication, you split them up into the two parts, and then you're able to decompose into the determinant. So we'll stop here for now. The next talk is going to be on affine space. So we're going to be finally leaving Euclidean space, and we're going to look at a new type of geometry, a new kind of land to live in. So this will be a fun little thing to learn. So I will see you in the next video.